Welcome. This video covers section 1.1, which is the nature of mathematical reasoning. In this video, we will talk about two different types of reasoning. We'll use inductive reasoning to make conjectures. We'll find a counterexample to disprove a conjecture. We'll explain the difference between inductive and deductive reasoning. We'll use deductive reasoning to prove a conjecture. First, there are two types of reasoning. That is, inductive reasoning, which also is known as induction, and deductive reasoning, which is known as deduction. Inductive reasoning is the process that arrives at a general conclusion based on the observation of specific examples. So specific examples goes with inductive reasoning. It involves looking for patterns and making a conjecture, which is basically an educated guess. Let's do one together. A game show host provides the following string of numbers: 1, 2, 4, 5, 7, 8, 10, blank, blank, blank. The first contestant who can continue the pattern and fill in the 3 blanks correctly will win $4,000. That would be awesome. And an 18-month supply of rice-a-roni, the San Francisco treat. Use inductive reasoning to find a correct answer. All right, so I'll give you a moment to try to see what's going on with this pattern. And remember, you are in charge of the video, so you can pause it at any time if I'm going too fast, and you can also rewind it or fast forward it. It's up to you. You are in control. Okay, so when I look at these numbers, I can see that they are increasing, and it could be multiplication, it could be addition, could be some kind of pattern of that. So really, I'm just kind of trying to figure out what that pattern is, right? So I know to go from 1 to 2, we could multiply by 2, and then 2 to 4, I could multiply by 2, but then that breaks apart when I do this one. And so at that point, I would say times 2 is out because it doesn't continue on. So I would probably see how is it increasing with addition. So from 1 to 2, that would be plus 1. And from 2 to 4, that's plus 2. And then from 4 to 5, that's plus 1. And then from 5 to 7, that's plus 2. And then from 7 to 8 is plus 1. And then from 8 to 10 is plus 2. Okay, so that's kind of a pattern I see, right? Because it's plus 1, plus 2, plus 1, plus 2, plus 1, plus 2. Okay, so I just need to add 1, and then add 2, and then add 1. All right, so that would be how I would solve this. And our text will give you an explanation as well. So their explanation is, to find patterns in strings of numbers, it's often helpful to think about operations that can turn a number into the next one. In this case, we can use addition to find a regular pattern, plus 1, plus 2, plus 1, plus 2, plus 1, plus 2, etc. So the pattern seems to be add 1, then add 2, then add 1, then add 2, etc. So a reasonable conjecture for the next 3 numbers is 11, 13, and 14, which is also what we came up with, so that's great. All right, so I'm going to give you a few to try, and then we'll move on to the next part. So use inductive reasoning to find a pattern and make a reasonable conjecture for the next 3 numbers in the sequence. Once again, feel free to pause the video if you would like to come up with that. All right, so for number 1, I can see that it's increasing. From 7 to 10 is plus 3. From 10 to 16 is plus 6. 16 to 25 is plus 9. 25 to 37 is plus 12. And then plus 15, plus 18, plus 21. So you can see that the pattern is we're adding 3, and then we're adding 3 more to that. So like I go from 3 to 6 to 9 to 12, 15, 18, 21. So it's going to be plus 24, plus 27, plus 30. All right, so let's see. So 91 plus 24 is 115. And then plus 27 is 142. And then plus 30 is 172. All right, so that would be my conjecture there. This next one is a little more complicated. So I'm going to try to use different colors here. So from 15 to 28, we are increasing. And we're increasing by 13. So this is plus 13. But then from 28 to 17, we are decreasing. And that would be by 11. And then from 17 to 25, it looks like it's increasing by 8. 25 to 19 is decreasing by 6. And then 19 to 22 would be increasing by 3. And then 22 to 21 is decreasing by 1. And then 21 to 19 is decreasing by 2. And then 19 to 23 is increasing by 4. And then 23 through to 16 is decreasing by 7. 16 to 25 is increasing by 9. Okay, so let's see what kind of pattern we have. So for red, 13 and 8, that is minus 5. 8 to 3 is minus 5. 3 to negative 2 is also minus 5. And then negative 2 to negative 7 is minus 5. Okay, so that part is going to be minus 5, lower than like the previous, right? So the next thing would be negative 7 minus 5, which would be negative 12. So 25 minus 12 is 13. And then you can see in blue, we have negative 11, negative 6. That would be increasing by 5. Negative 6 to negative 1 would be plus 5. Negative 1 to 4 is plus 5. And then 4 to 9 is plus 5. Okay, so then I need to basically, it'll increase by whatever this number is, plus 5. So 9 plus 5 is 14. So I would add 14 to 13, and that would give me 27. And then I've got to do this negative 12 minus 5, which would be negative 17. So 27 minus 17 is 10. All right, that one was pretty intense. I don't think we give you any that are that crazy, but it is good to practice those, right? Okay. We're now going to move on to a different type of problem, and that is example 2. We're going to use inductive reasoning to find a pattern, but this time we're given figures. Okay, so we have this figure. I don't really know what that is. It looks like maybe it's a little fish or something, I guess. It's kind of random. But anyways, we're going to try to figure out the pattern. So I'm going to look at this, and I'm just going to kind of think about what's happening here. So here I have it's face down. Like, so if I think about like this, let's pretend this is like the fish, right? Then I would say that if it looks like that, I'm going to say that it's facing down, and the circle is filled in. And then on the next one, it's facing to the left. The circle is filled in. And then for this third one, it's facing up. So if I think of this as its face, right? Pretend this is a little fish here, right? It's facing up, and it's filled in. And then it's facing right, and it's filled in. Okay, so then I have down again, but open, left, open, up, open. And then I can see by this pattern that the next thing that's going to happen is it's probably going to be going to the right, and it's going to be open. So this is what the figure would look like. All right. So basically, they have their own little solution that they want to tell you as well. So it says, in the first 4 figures, the flat part goes from facing up to right, down, then left. There's also a solid circle in each figure. This sequence then repeats itself with an open circle in each figure. So in the next one, the flat part should face left and have an open circle, which is kind of like the same thing that we talked about. All right, so let's move into our next example, which is to use inductive reasoning to make a conjecture. So this says, when 2 odd numbers are added, will the result always be an even number? So when 2 odd numbers are added, will the result always be an even number? Use inductive reasoning to make a conjecture. How many pairs of number would you need to try in order to be certain that your conjecture is true? Okay, so let's start. We'll start first with the letter A. And I'm going to show that when I add two odd numbers together, so when you think about odd numbers, let's just talk about odd numbers for a second. Odd numbers would be like 1, 3, 5, 7, 9, 11, 13, etc. Even numbers are 2, 4, 6, 8, 10, 12, goes on forever, right? Okay, so if I add two odd numbers together, such as 1 plus 3, I get 4. If I add 3 plus 5, I get 8. Okay, so far it's checking out. If I do 7 times 9, I get 16. And if I want to be fancy, I could say, what about 100 plus, oh, sorry, not 100. I could say 101 plus 1, that would be 102. And then I could say maybe 97 plus 3, that would be 100, right? I'm just showing that when I add two odd numbers together, I get even. And so I would say that this is probably true, but letter B is asking, how many pairs of numbers would you need to try in order to be certain that your conjecture is true? So what I want to tell you about this is that there's an important point about inductive reasoning. You can try specific examples all day and always get an even sum, but that can never guarantee that it will always happen. For that, we're going to need to talk about deductive reasoning, which we're going to be studying in just a little bit. Okay, so basically, how many pairs of numbers would you need to try in order to be certain? An infinite amount. And it's kind of like a trick question. We cannot be certain. So we cannot be certain just from specific examples. Because the thing is, I could show you 1,000 specific examples, and you could just show me one counterexample, and the whole entire thing would be falling apart, would fall apart. All right, so that's what we're going to talk about soon. We're going to be talking about that deductive part. All right, and here we go. I didn't realize it. I had the solution on the next slide. So first, let's try several specific examples of adding two odd numbers, which is what we did. Since all the answers are even, it seems reasonable to conclude that the sum of two odd numbers will be an even number. However, as I was saying, a very important point about this is you can try specific examples all day and always get an even sum, but we can never guarantee that that's always going to happen. For that, we're going to need deductive reasoning, which we'll study in just a bit. All right, so we're going to talk now about counterexamples. As I was mentioning before, it just takes one counterexample to basically prove that the conjecture is false. So to find a counterexample, you're going to start with a number or object that matches the premise of the conjecture. Pick this in a way that will give you an incorrect response. All right, so this is kind of fun because you're going to try to disprove things. Remember, one counterexample is enough to show that a conjecture is false. So we just need one counterexample and the conjecture would be false. But one positive example is never enough to show that a conjecture is true. In fact, in most cases, even 100 positive examples wouldn't do it. That's why we'll need a different type of reasoning. Okay. So we are going to find a counterexample that proves that the following conjecture is false. It says a number is divisible by 3 if the last two digits are divisible by 3. Okay. So we're going to try to disprove that. And if you think about what does it mean to be divisible by 3, then that just means that you divide evenly into 3. For example, numbers that are divisible by 3. So we're going to want to talk about that first, right? So numbers that are divisible by 3 would be 3, 6, 9, 12, 15, 18, 21, 24, 27, etc. Basically, you can divide it by 3 and it goes into it completely. You won't have a remainder. So an example of 9 divided by 3 is 3, that means that 9 is divisible by 3. But if I had something like 17 and I tried to divide that by 3, then that would be I would have a remainder. It doesn't go evenly in to that. So like I'd have a remainder of 2 if it was 17, right? So we're going to pick a number that is basically divisible by 3, but the last 2 digits are divisible by 3, but the number itself is not. Okay, so for example, I'm gonna like pick on 27. So 27 is divisible by 3. So to test this conjecture, I'm going to put a 1 in front of the 27. So this conjecture says that if this part right here is divisible by 3, then the whole thing is divisible by 3. But I don't think that's true, because if I divide 127 by 3, let's see if we have a remainder or not. So 4 times 3 is 12. I bring down the 7, and that would be 2. 2 times 3 is 6. That's a 1. So we have a remainder of 1/3. So no. And my counter example would be 127. That would be an example of a counter example. And you could even type that into your calculator. And I did that by hand. But if you do 127 divided by 3, notice you're going to get 42.333333. And the fact that we have a point anything would say that it's not divisible by 3. Okay, so that's an example of what we call a counter example. Now we're going to move into, finally, deductive reasoning. Deductive reasoning is the process of reasoning that arrives at a conclusion based on previously accepted general statements. It's based on overall rules, not specific examples. All right, so what I tell my students is the 2 main differences between inductive and deductive is that inductive deals with specific examples, whereas deductive is based on general statements and rules. All right? Okay, so let's get started with deductive reasoning. Okay, so let's do an example together. It says, consider the following problem. Think of any number, multiply that number by 2, then add 6, divide the result by 2, next subtract the original number. What is the result? Use inductive reasoning to make a conjecture for the answer. Use deductive reasoning to prove your conjecture. Okay, so let's think of a number. We'll do this together. All right, so let's let the number be 12. Make this a little smaller here for you. Okay, so our number will be 12. Okay, and you could start with any number. I'm going to pick 12. I'm going to now perform these operations. I'm going to multiply by 2. All right, so 12 times 2, or 2 times 12 is 24. Okay, then I'm going to add 6. So 24 plus 6, which is 30. All right, and then I'm supposed to divide the result by 2. So 30 divided by 2 is 15. Okay, and then I'm supposed to subtract the original number. All right, so that would be 15 minus 12, right? 12 is my original number, and that gives me 3. All right, so my result after all of that is 3. Okay, well, let's try one more. Let's try a different number and see what happens, all right? Let's try something kind of out there. Let's try 43, okay? So I'm just going to draw lines here to show that I'm going to do all the same operations, all right? So I'm going to start with 43 this time, and feel free to do whatever number you want. I'm going to multiply 2 by 43, which would give me 86. I would do 86 plus 6, which would give me 92. I'll do 92 divided by 2, which is 46. I'll do 46 minus 43, which is 3. So at this point, we might be tempted to conclude that the result is always 3, but this is just a conjecture. We've tried only a few of infinitely many possible numbers, not to mention the fact that we've chosen only whole numbers. What about decimals, fractions, negative numbers? As usual, when using inductive reasoning, we can't be completely sure that our conjecture is always true. But at this point, it seems like it would at least be worth the effort to see if we can prove that our conjecture is true. Okay, so the problem with the inductive approach is that we can't check every possible number. Instead, we're going to choose an arbitrary number and call it A. Think of it standing for any old number. If we can show that the result is 3 in this case, that will tell us this is the result for every number. Remember, we'll be doing the exact same operations just on an arbitrary number A. This will require some basic algebra skills. All right, so let me show you what that would look like. Okay, so now we're going to be using deductive reasoning. All right, so let's get started. So we're going to have the same example, but we're basically going to do deductive reasoning. We're going to use part B. So we're going to use an arbitrary, we're going to call an arbitrary number, and we're going to use A. Okay, so A is just some arbitrary number because we can't check every single number, but we can declare, hey, look, A can be any number, right? And we're going to call it A. And our hope is that we end up with A3 as our result. Okay, so we've got to use some algebra here, though. So let's let our number, so we're going to go through that same process, but our number is going to be A. We're going to multiply it by 2, right? So if I do A times 2, that's just 2A. Then we're going to add 6 to it. So that would be 2A plus 6. Then we will divide by 2, right? So let me do this in a different color here. So we'll have 2A plus 6 divided by 2. Okay, and when we divide it by 2, that 2 is going to each piece here. So it's really going to be 2A over 2 plus 6 over 2, which reduces 2A plus 3, right? Because those 2's would cancel out, and 6 over 2 is 3. Okay, then we will subtract the original number. Well, our original number is arbitrary A, right? From the beginning, right? So we're going to be basically subtracting A because that's our number. So we have this A plus 3, but now we're going to subtract A. And when we do that, look what happens. We end up with our result is 3, right? Because the A, positive A minus A, cancels the A's out, and we just have 3. Now we know for sure that the result will always be 3, and our conjecture has been proved. Right? That's exciting. That means that you could put any number in there and it would always work because we were able to prove it using deductive reasoning. Okay, let's try another one. All right, so we're going to consider the following problem. We're going to pick a number. We're going to do all these things to it. We're going to do a few specific examples, and then, of course, we will do the deductive reasoning as well. Okay, so pick a number, any number. What number do I want to pick? Let's see. I'm going to pick 12 again. Why not? Okay. I'm going to add 50 to 12. All right, so 12 plus 50 is equal to 62. I'm going to multiply that by 2, which gives me 124. Then I'm going to subtract the original number. So minus 12 is equal to 112. So my result is 112. Okay. Now, okay, so I started with 12 and I got 112. Okay, so let's do that again, and I'm going to do it right next to it. Okay, so let me draw like a little space here. There we go. Okay, now let's try another number. Let's try 50 and let's see what happens. So if I try 50, just draw lines so I have a little more room here. Okay, so I'm going to try 50. Okay, 12 plus 50. Oh, I'm sorry. 50 plus 50, my bad, because we're adding 50. Okay, 50 plus 50 is 100. And then I'm supposed to multiply that by 2. So 100 times 2 is 200. And then I'm supposed to subtract the original numbers. So 200 minus 50 is 150. And so my result is 150, right? So I started with 12 and I got 112. I started with 50 and I got 150. What do you think is happening? What would you say? I think that I would say inductively that my conjecture would be that the final answer is 100 more than the original number. Okay, but we want to actually use deductive reasoning to prove that. Okay, so we're going to try to prove that that's always going to work, right? So to do that, we're going to let A be an arbitrary number. Sorry, my handwriting is not very pretty right now. We're going to let A be an arbitrary number. We're going to perform the operations, okay? So I'm going to do this up here. This will be good. Okay, I'm going to do it to the left. So we have A. We're going to add 50 to A. We're going to multiply by 2. So that would be 2 times A plus 50. Notice that I would want to put that part in parentheses. And then we're going to subtract the original number. So if I have 2A plus 50 minus A. So I'm going to have to use my distributive property, right? So 2 times A is 2A, and 2 times 50 is 100. So I have 2A plus 100 minus A. Well, 2A minus A is 1A plus 100, right? So 2A plus 100 minus A. The A's go together. 2A minus 1A is A plus 100. All right, so that shows that our conjecture is right. The final answer is always 100 more than the original answer. All right, so those are kind of fun, right? Next, we have comparing inductive to deductive and determining which one it is. So it says the last 6 times we played our arch rival in football, we won. So I know we're going to win on Saturday. Did I use inductive or deductive reasoning? Okay, since they're talking about specific examples, it's definitely going to be inductive, which is what it says down here. This conclusion is based on 6 specific occurrences, not a general rule that we know to be true. No team wins every game. Okay, let's try one more. The syllabus states that the final average between 80% and 90% will always result in a B. If I get a 78% on my final, my overall grade will be an 80.1%, so I'll get a B. Okay, so did we use inductive or deductive? Well, this is definitely deductive because this is like a rule, right? This is a general statement, it's the rule, and the grade here fits in between that, right? So this is definitely would be considered deductive. Okay, even though we're talking about a specific grade, we're using a general rule to determine. All right, I hope this video helps you understand section 1.1. I hope you have a great day. Bye.